thanks for the introduction. So I'm Jordan, and this is joint work with Sesha, and we're starting at the basics, doing some of the simplest inference problems you could do, is working with binary data and hypothesis tests. It turns out that it's still quite a challenge with differential privacy. So there's been a good amount of previous literature on hypothesis testing and differential privacy. It sort of started with Vu and Slavkovich on binomial data tests. And that's sort of the jumping off point for our research, is going back to this simple problem and working with it in a very theoretical framework. But there have been lots of other hypothesis testing works on different types of data, such as contingency tables, normal data, linear regression. Recently, there's been a really interesting paper by Kanan et al. On simple hypotheses, which we'll hear about in just a moment. And then there's also been some interesting work on asymptotic tests by Wang et al. So the structure of this talk, our motivation is to work out uniformly most powerful tests. So this is, in classical statistics, the gold standard of the hypothesis test that we'd like to find. I'll define it later. And these are really fundamental in classical statistics. They're closely related to sufficiency, likelihood inference, and we'll see how we can use these hypothesis tests to produce confidence intervals as well. So our initial goal is to develop hypothesis tests and p-values. We're working with binary data under differential privacy. So some of the highlights of our contributions. So we're going to produce the first UMP tests under the framework of differential privacy, and this is for Bernoulli data. Along the way, we develop a new distribution, which we call the Tulap distribution for truncated uniform Laplace. And this extends the staircase and discrete Laplace distributions, also known as the geometric distribution. And we show that our tests can be written in terms of this distribution that we've developed. From this, we can derive p-values that agree with our tests. We show that, as we claim in our proofs, that this does outperform other tests in the literature. And then we show how we can take our p-values to produce confidence intervals that also have optimal properties. So the notion of differential privacy that we're working under is epsilon delta dp. So we're going to consider our database to be a vector of entries. Each entry is from one individual, where we're assuming that n is fixed and known. And so we're just going to be swapping one entry in this list. We think of a mechanism as a set of probability measures. And so we are given our database. We're drawing from some distribution. And so differential privacy says when I change, let's see. OK, so if I change one entry of x, then I want this distribution to only change by a small amount. And so the idea is we want the distributions to be similar. So what about hypothesis testing? So generally, a test is trying to determine the value of a parameter that we don't know what it is. So we're trying to learn about theta, and it lives in some parameter space, capital theta. And we're trying to decide whether it lives in theta 0 or theta 1, which are disjoint subsets of big theta. So we call theta 0 the null set. So this is sort of your assumption beforehand, and then the alternative would be, oh, we found something really interesting. This is not what we expected. We get to write a paper about it. And so we're going to model a test as a map from the set of databases to 0, 1, where this value in 0, 1 represents the probability of rejecting. So that's where we're going to incorporate our randomness for differential privacy, is in this random decision of whether we're going to accept or reject. So typically in classical statistics, we have deterministic tests. And so if this is, the rectangle is our parameter space, then we might have, at some cutoff point, we would go from never rejecting to always rejecting. Oh, sorry, I misspoke. So this is the space of databases. So for some databases, you would never reject. In some databases, you would always reject. But because we need to incorporate randomness, Instead, we have some gradient where there's always a small probability of rejecting, and that probability increases as we move to the right. And so the actual output would be we would flip the coin with probability phi, and then that will output either accept or reject. Two more concepts of hypothesis tests. We have the size, also known as the type 1 error. And this is the probability of accidentally rejecting when the null was actually true. So typically, we limit the size to a predetermined value, such as 0.05, or you could do something smaller. And so this is a hard threshold that we're going to keep fixed. And then, given that we've limited the type 1 error, we want to have the most powerful test possible, which means that when the alternative is true, we want to be able to reject as much as possible. And so we say the power at some value theta is the probability of rejecting when we're getting data from that parameter value. OK? So we're going to look at tests phi that satisfy differential privacy. We're going to fix the size and try to optimize the power. So in particular, we are working with binary data. So each person tells us a 0 or a 1, and we've got this vector of 0s and 1s. We're going to model these as independent Bernoullis. And so we're assuming there is some underlying proportion theta that we're trying to infer. We have a technical lemma that says that even in differential privacy, we can get away by just recording the number of 1s. So we just have to work with x now. And x is now distributed as binomial, which leads to the title of the talk. We're working with this binomial distribution from now on. And so the test that we're looking at, for the moment, we're just going to release the decision accept or reject. That's the only output of our mechanism. Later, we'll see if we can do more than that. And these two decisions, accept and reject, have probability phi and 1 minus phi. So in the setting of differential privacy, our notion is in terms of the probability of all possible outputs and all possible adjacent databases. But because our problem is so simple, it turns out we can actually write down all of these inequalities in terms of our function phi. So the only outputs of interest, the only sets B of interest, are reject or accept. And these have probabilities phi and 1 minus phi. So we can replace all the p of b's with either phi of x or phi x minus 1. Equivalently, you could do x and x plus 1, but you can rearrange it the way to get this. And then so the only adjacent database is the value x increases or decreases by 1. And so we can take all these abstract inequalities and write down these 4n inequalities here. Now, it's going to be convenient later to arrange these in a slightly different way. And so we're going to show that, or we're going to write it in a way so that we can define phi recursively. So if I take phi of 0 given, then I have 2 upper bounds and 2 lower bounds on phi of 1. And so I can relate phi x in terms of phi x minus 1. And so I could choose phi 0, and then I have a range of values I can pick for phi 1, and then I have a new range for phi 2. And as long as I satisfy these inequalities as I go along, once I've picked all 0 through n, then that thing is still differentially private. So we're going to study tests phi that satisfy all these inequalities, which is equivalent to satisfying differential privacy. So we'll denote that set by fancy d. We'll keep track of the epsilon delta and the n. OK, so our goal here, or our initial goal, is to determine the most powerful test among these differentially private tests phi. So we're looking all over the set, the things that satisfy those inequalities. We're fixing the size alpha, so the type 1 error. And the hypothesis that we're going to test for the moment is going to be the null is that theta is less than some value, and the alternative is that it's actually larger than the value. So perhaps we're collecting data on whether you have a disease or not. And it's been previously believed that the prevalence of disease is some amount or less. And we're saying, oh, no, there's actually an epidemic. So we warn the alarm and say that actually it's higher than we thought. in which case we reject. So the way we're going to build this. So first we'll think back to classical statistics. This is one of the first problems that you would learn about in a statistics inference class. And you learn that you're supposed to use the Neyman-Pearson lemma to figure out the optimal test. And what Neyman-Pearson lemma says is that you go along, and at low values of x we have no evidence that we should reject. High values of x you have a lot of evidence, and so there's a point where you jump from 0 to 1. And maybe there's a fuzzy point in the middle. But there's essentially this hard line where we go from never rejecting to always rejecting. And Neyman-Pearson is sort of a greedy solution which ends up being optimal. So we can't do the same thing because a jump from 0 to 1 would violate the upper bound that we have here. We're only allowed to jump by some amount. So let's take the spirit of Neyman-Pearson lemma, where we want to be greedy, but we're going to do it one step at a time. So we'll take phi of 0 as something predetermined. I don't know how to choose it yet. And now I'm going to have two upper bounds. For phi of 1, I'm going to take the smallest, meaning the largest valid value of phi of 1. And so here, once I've chosen phi 2, I see that I have these two upper bounds given by these two equations. And so I'm just going to go along picking the largest value I'm allowed to while still achieving differential privacy. And so this is sort of an intuitive solution, and it turns out the intuition is correct. And using a similar proof as Neyman-Pearson, you can show that this is in fact the UMP test. But it's not super satisfying because it's sort of ad hoc, we're going one by one. It'd be nice to have a closed form solution of this test. So then we had an insight that this test phi, it's an increasing function, monotone increasing from left to right. And it takes values between 0 and 1. So it's actually the CDF of some random variable, meaning cumulative distribution function. So there's some random variable that corresponds to this increasing function. And it turns out that we figured out what it is, and we called it the Tulap distribution. So with parameters related to epsilon and delta, we're able to write the optimal test in terms of the CDF of this distribution. So what is this Tulap distribution we found? So an intuitive way to understand it is you can take a discrete Laplace. This is the same as the geometric mechanism. And a uniform between -1/2 and 1/2. And you add them together along with the center, which is a constant m. And then what you get is this staircase type distribution. It's exactly the staircase. But what we do is to get the delta, the epsilon delta, we chop off the tails at certain quantiles where q was related to epsilon and delta. And so we call it the truncated uniform Laplace because that's how you construct it. And so what this gives us, it gives us a few really nice things. First of all, it gives us a closed form for this UMP test. That's nice. But it also turns out that we're able to get p-values by using this distribution. So how is that? Well, it turns out that we can write our test phi as a post-processing of x plus a noise value from this Tulap distribution. So phi is the CDF of the Tulap evaluated at x. The CDF is exactly just the probability that x is less than n. Rearranging this a little bit, we see that we can release x plus n, where n is from Tulap, and then just evaluate the this probability afterwards. And to remind you what a p-value is if you have a bunch of hypothesis tests at different sizes alpha, the p-value is the smallest alpha such that we would output reject. So you could do a search, maybe a binary search, and you could figure out what's the smallest value of alpha that you can get away with rejecting. That would be the p-value. But it turns out there's an even more efficient way to go about this for this problem. And so if we have our data x, we then produce our noisy summary statistic where we take x, we add a Tulap. So we have this here, z given x, is our summary statistic. So first of all, z does satisfy epsilon delta differential privacy. And then an easy way to compute it is in terms of the PMF of the binomial down here and the CDF of the Tulap. You take an inner product. It's as easy as that we're able to compute the p-values. So these p-values satisfy differential privacy because they're post-processing z. And they agree with our UMP tests that we developed earlier. So an important observation here, we set out to only release, accept, or reject. And at the same level of privacy, we found that actually we are able to release the summary statistic and produce p-values, which we never intended to be able to do. So that's quite nice. And it turns out that we're able to get even more out of this, which we'll see going on. First, just a sanity check. So we claim in the theorem that this was the most powerful test. Well, so in Vu and Slavkovich, they gave a normal approximation test, and we're just going to see that, in fact, we are able to get higher power than their test. We're still bound above by the non-private case. And more interestingly, we have exact type 1 error up to numerical inaccuracies, but the normal approximation has varying type 1 error because it is an approximation to the test. Okay, so what else can we do? So the next thing we'd like to do is two-sided tests. So we were working at one-sided hypotheses where we said the null was theta's less than something and the alternative was that theta was bigger. Well, it's also common to look at things like testing theta is equal to theta 0 versus not so. So the first thing is we know in classical statistics that there is no uniformly most powerful test in this setting. And the problem is that you could take the most powerful right-sided test and the most powerful left-sided test, and they would dominate in different regions. So sort of the space of options is too large. There is no optimal thing. And so we need to reduce the search space. And what's commonly done in classical statistics is to impose the condition of unbiasedness. So unbiasedness is not quite the same thing as you might think for point estimates. The idea of an unbiased test is that we want to make sure that under the null, the probability of rejecting is always smaller than anything in the alternative. So any unbiased test seems fairly reasonable by imposing this condition. There are still good tests that are ruled out by this. It might be that it dips slightly below in the alternative space and we're missing out on those. But in classical statistics, this is what's commonly done. And so by imposing this, we're now able to find a UMP unbiased test. Right, so this unbiasedness, the idea is that we want to be rejecting more often in the alternative than the null, no matter which values we take from the alternative or null. So using a similar construction, we're able to get a UMP unbiased alpha test among our DP tests. And the argument is similar. So without privacy, we could imagine, I don't have an image, but imagine we have our set of x's. So for large x's or small x's, we would eventually reject with certainty. And if it's moderate near the null, then we wouldn't reject. So the idea here is that we're going to have some center k, and then we want to increase as much as possible in both directions. And that's what we see here. So there's some k, which we'll have to figure out what it is. And then we're going to be a Tulap CDF on either side of it, where we're increasing as much as possible, subject to the DP constraints. And so we can write in this form as a piecewise, where each evaluation is the CDF of the Tulap. And then we have a few more conditions we need to make sure. So the second condition is just checking that it is size alpha. So that's quite standard. And this other one is going to impose the unbiasedness. So this condition, you'll see if you read a textbook on classical statistics. So it's basically checking that the correlation or the covariance between x and phi of x is 0. And it turns out that that is equivalent in this setting to checking for unbiasedness as we defined it. So if you can find your k and m such that these two equations hold, then it is the UMP test, and we can show that there is always a solution. So it's just a matter of finding it. So as I said, this is what these tests look like. So they're centered at some k, and then they increase on both sides. And we're going as the epsilon is increasing, we get closer to the jump functions that you would get without privacy. So without privacy, we would just be 0 in the middle here, and then 1 outside. And so we're converging to that as the privacy goes, or less privacy, higher epsilon. So this unbiased test is also a function of the Tulap. And so theoretically, you could compute the p-values. But the problem here is that the k and m depend on alpha. So it's sort of a pain to do that minimization problem. There isn't a nice closed form for the p-values like there was in the one-sided case. But we're able to get something quite close. So we notice that k, although it depends on alpha, as the sample size increases, k gets very close to n theta 0. So the center here where we change sides is close to the mean of the binomial. And as the sample size increases, it converges to that. And so what we could do is we could just choose k as n theta 0, and still, so that would eliminate this constraint, and then we would still set the size as alpha. And that's what we do here, and that we're able to get the p-value from that construction. And so it's still a valid p-value, meaning that the corresponding test has the exact size. It's just that we're giving up on the unbiasedness, and we're just asymptotically unbiased instead of exactly unbiased. And we'll see in the simulation in a second that it's a really close approximation. So here we have simulation. So there's 4 curves here. So what are the 4 curves? So we have the one-sided tests in green and blue. So this is not the one you want to pick, because this one is testing. So the null is that theta is to the right of the value, and so we get less and less evidence as we observe things to the right. The left one would be the most powerful test for testing that theta is less than it versus the right. So that's an upper bound for any two-sided test. And then the 2 curves here in red and purple are in red is the UMP unbiased, and the purple is our approximation. And this is for n is 30, so as the sample size increases, it gets only closer. And this is just a zoomed in version around 0 to 0.2 to see what's happening with the curves. And we see that the purple, the approximate test, is just a slight shift of the red UMP unbiased one. Okay. Any questions so far? Okay. Hopefully I haven't lost everyone. So the last part of the talk is discussing how we can turn these tests, which is we've just been focused on hypothesis tests and p-values, and showing how we can leverage those to produce confidence intervals. So a confidence interval is a pair of random variables. So although they depend on the data x, we're also going to sense that a and b have additional randomness for differential privacy. And a confidence interval has coverage gamma if under the true value theta, the probability that we contain theta is at least gamma. So this is like what Vijesh was talking about earlier. We want to make sure that these are sort of valid or honest confidence intervals. So we're going to insist that this probability holds strictly. And the way we're going to go from p-values to confidence intervals is by this fact that if you have a p-value where the null is theta 0, it doesn't actually matter what the alternative is. You can always produce a confidence set by taking all the theta zeros that you failed to reject. So if the p-value is larger than alpha, then we didn't reject it. So those are sort of the plausible values of theta, and we'll keep all those. And they could have a very funky shape, but if you pick nice p-values, you get usually one-sided or two-sided confidence intervals. And so We already have differentially private p-values, so we can post-process those to get differentially private confidence intervals. Well, it'd be nice to have an optimality criterion. So we call these uniformly most accurate confidence intervals. So we choose a coverage, and we're going to hold that fixed. And then what does this concept mean? So under a true theta and a false theta 0, we want that the probability that we're covering the false value to be smaller. Meaning that on average, this one's going to be a smaller interval because it's capturing these incorrect thetas less often than the C prime is. So this might seem a little contrived because it is. So this is designed to be in one-to-one correspondence with the uniformly most powerful tests. But it does tend to produce the thing we want, which is smaller confidence intervals. But it doesn't do it in a very direct manner. But because of that correspondence between UMP tests and UMA confidence intervals, we're able to show that taking our one-sided p-values and producing the confidence interval gives us the DP UMA confidence interval with exact coverage. So these are the lower bounds instead of a two-sided interval. Yeah?
What's the definition of, what's the distribution again, the Tulap? It's a geometric distribution.
Plus a uniform from -1/2 to 1/2. And then you might chop off the tails.
Depending on
delta. Yeah.
And so, yeah, I guess I'm a little confused. I mean, does the uniform -1/2 to 1/2 do anything?
So it doesn't do anything for privacy because we could basically round it off and get back what you would have from just adding the geometric.
Right. So it's like a post-processing of...
Yeah, so it's sort of, we had to make a decision where to add in this, either have additional randomness in the phi or to put the noise into the summary.
I see.
And either one works just fine. We just found it was easier to sort of write it up in this manner. Any other questions? Okay. So that was our one-sided confidence intervals. So what about two-sided? Well, again, the space is too large, so we can't get UMA two-sided confidence intervals. We need to restrict to a smaller set. Well, just like there are unbiased tests, we're going to make a concept for unbiased confidence intervals. Again, this is done in classical statistics literature. And unbiasedness means that the probability of covering a different parameter value is always smaller than the probability of covering the true parameter value. So again, it's sort of a reasonable thing to assume, but maybe not the first thing you'd think of. So then this ugly thing is the p-value of our UMP unbiased test. So it's literally the smallest p-value such that the corresponding test statistic is larger than the corresponding threshold. And K and M, as I mentioned earlier, do depend on alpha, so this is sort of a pain to compute. But it does have the property we want, so it's the DP UMA unbiased confidence interval. But in practice, I don't think it's worth computing this. Rather, we could take our asymptotically unbiased test, for which we have easy to compute p-values, and we would invert that to get an approximately unbiased two-sided confidence interval.
So here, I guess I'm a little surprised that K depends on alpha.
Yeah.
I mean, so if I understand correctly, your Z is a noisy.
Yeah, noisy mean.
A noisy mean, and now you're looking at. Again, the setting is you're trying to distinguish theta 0 from like not
so, yeah.
Not theta 0.
Right.
And it's not the case that setting like K to be whatever theta 0.
And theta 0 would be the natural thing.
And that's not optimal?
It's not unbiased. So here's I could draw a picture, maybe. If theta is a half, then it's exactly right. But if theta is not a half, then so let's So here's 0 and 1. And let's put theta over here. Maybe let's say this is the picture of x's. So the binomial looks kind of like a normal, except it has a much longer tail on one side. And then the tests look like things like this or U-shapes. And different alphas will give different shapes. And we want to choose the center where to place this such that the covariance is 0. But the different shapes might require us to put it here versus slightly to the left or slightly to the right. And so it's all about this unbiasedness. But since the unbiased isn't really crucial, by taking it to be n theta 0, you get a good solution. You just can't prove the same sort of things about it. Any other questions? Okay. I think that's the end. So some highlights. So in the initial part of the talk where we were developing our hypothesis tests, so emphasizes the first result to give exactly UMP tests in the differential privacy framework. We developed this new distribution. It's sort of an extension of the staircase distribution, but it has this truncation for epsilon delta. And the idea of viewing the hypothesis testing and differential privacy in terms of the phi function, these linear constraints, provides a nice perspective. You could even view it as a linear programming problem for simple hypotheses. There are limitations. So the Bernoulli situation is incredibly nice, and it's unreasonable to expect things to work out so nicely in other places. In particular, these linear constraints don't help if you have continuous or complicated data. The Neyman-Pearson argument might not extend, and then cannot at all based on, is this Renner and Nassim? So they argue that this sort of uniformly optimal property that we're deriving here is inherent to the binary situation, and so these UMP tests likely are not going to exist in general scenarios. And then based off of our hypothesis testing framework, we did get confidence intervals, p-values, and although I didn't talk about it, there's an idea called a confidence distribution, which is sort of the frequentist version of a posterior distribution. I'd be happy to chat about that afterwards if you're curious. Some references, and an early version of this based on just the one-sided tests was published in NIPS 2018, and a full version of the talk is on the archive. So thank you for your time.
I guess I'm joining the session. Any questions for Jordan? Yeah, go ahead.
Yeah, this is awesome. We have something that works for n equals to 30.
Yeah.
And I guess the natural question is that you also mentioned this in the limitations, but I'm still wondering, like from the statistics class that I learned, all this UMP and stuff, they generically extend to estimating parameters and constructing tests for exponential family distributions. But this is a much more restricted setting, and what are the things that you have in mind to relax the UMP definition a little bit so that you can talk about this kind of stronger optimality guarantees and just being minimax? I mean, getting exact minimaxity for more general problems is interesting problem itself, and I think it's still open. But what are the things that are related to UMP that you can talk about?
That's a good question. So over last summer, I was working with Salil, and we were trying to do difference of binomials, and we're looking at that testing problem. So naively, I thought that it would be a simple corollary of what we're doing here. It turns out that everything breaks right away. And in fact, the first week, we did a simulation that showed that there is no UMP unbiased test for that. So yeah, we were sort of exploring minimax concepts or other things. We didn't really come up with a good answer, but we started thinking about it in terms of sample complexity, as people do, but we're still insisting on the exact size and trying to get the power. So I'm not sure if there is a good answer right now of how to extend these concepts of UMP when there isn't one. But I think it's a worthwhile thing to look into.
So what's
Oh, I was just going to point out a similarity to an older paper of Ghosh, Rough Gardens, and I'm getting the last name wrong. Sundararajan, thank you. Where they did something, again, looking at binary data, using linear programming to come up with an optimal, like a class of algorithms, and they gave this sort of a class of problems for which they argued that post-processing the geometric mechanism is always the right thing to do. It's always the optimal mechanism. And so it's just like the first part where you explained how you derived the optimal test based on that sort of those linear constraints on the probabilities was felt very similar to that. And I think maybe some of the, like for epsilon 0, some of the results might, it sounds like there's a fair amount of overlap. Maybe not for the, not complete by any means.
Okay.
Do you want to mention some extensions to the median and testing for the median and the other?
Sure. So there's a bit more that we left out of the talk. So there are some distribution-free hypothesis tests that you can do on continuous data that have binomial test statistics. So one is the sign test, and the other is the median test. So the idea is for let's say the sign test, if we have paired continuous data, and we want to test if the median, say after treatment, is higher than before treatment, you take all the differences and then you count how many of them are positive. And then this is the count, and so it's binomial. And so you can apply these procedures. So it's not going to be optimal in terms of all continuous hypothesis tests for the problem, but in terms of the sign test, it would be the best DP implementation of that. And there's another one for the median test where they're not paired, but you have a before and after sort of treatment, two populations, and you're looking at the difference. You can do a similar thing. So.
Anything else? Thanks, Jordan.